This is our final study project, 3D printer filament change final study for IE3343. My name is Angela Caicedo. I'm the captain of the team, and I will be the first one in the speak to you. For the table of content, we have the introduction, the objectives, the methodology, the process description, data collection, the analysis, the findings, the recommendation, and finally the conclusions. So the purpose of a study is to measure and evaluate the time required to complete the 3D printer filament change process. A quick overview is we are going to analyze each step, beginning with heating the extruder, preparing the spoon, loading the filament, and finally starting the printer. And the importance is we want to show where the time is being spent, and we want to standardize and improve the process. So one of our objectives is to measure the time required to complete the filament change setup, identify any bottlenecks that it was discovered during the process, standardize the steps involved in the filament change process, and improve efficiency across the process. Now, Wyatt is going to talk about the methodology.
Hello, my name is Wyatt Hampy, and for our methodology, as Angela said, we identified how we were going to be tracking the 3D printing and reloading our filament spools, but the next part was how to more clearly identify where we are at tracking those times. We determined that we would go with a snapback measurement because each individual element had very clear and defined moments that we were tracking it, and that way we would have more accurate measurements of the individual elements. We did a direct time study using 10 total cycles, so each person in our group was able to cycle through and ensure that we had a little bit better variability and more consistency within our data. Before tracking any of the cycles, we broke it down into 4 to 10 Fergligs. That way we knew exactly what movements to make and when. That way we were consistent in our observations. In order to make these observations, we needed a few tools, one being a stopwatch in order to track the time that we took, and the other being a time study form in order to keep track of all the data that we had. For our methods and conditions, we made sure that we did this in a lab setting so we could have expert supervision and the best equipment that we could, making sure that both the equipment went unharmed and our personnel went unharmed as well. And once again, in order to create the best variability and most consistency, we made sure to cycle through each person in our group, giving each person 1 to 2 trials and creating our 10 observations.
My name is Elijah Whitman, and this is the process that we actually studied. And this is a big part of 3D printing. You have to do it every time you switch out filaments to print something new. So the first step was you would heat the extruder nozzle, and that involved going through some menus and setting the temperature to 240 degrees Fahrenheit. That involves some wait time on that, unless it was preheated. Then you would pick up the filament spool from its location, which could be right next to it or on another table. And you would, then what you'd have to do is actually cut the filament tip at a 45-degree angle. If it's a different angle, it doesn't work as well. And that's its own process involving snips. Then you also have to place the spool on the printer holder, which is up there on the top of the printer. And it has to be facing the right way, which is something that we didn't always get right, which would lead us later to think that training could help. Then inserting the filament into the extruder, which was oftentimes the most time-consuming process and the one with the most variability. You have to insert the end of the filament into the extruder and allow it to melt a little bit and pull it all the way through. And then you have to start the print, which goes back to the menus on the little screen that could be optimized. And then onto the data collection.
Hello everyone, my name is Syed Ali. So our data collection for the project, as we see here, there were multiple cycles that were recorded for each element. We had about 5 elements and about 10 cycles, so there was a lot of data that basically we summarized here. So the table is showing total observed time on this top row, total normal time on the second row, and then standard time on the third row. And as you can see from the numbers, our 5th element is giving us a very different set of numbers than all the other elements. This is because it took us longer for this element in particular, and it gave us numbers of 2.72, 2.232, and 0.246. And also at the bottom, our total standard time was calculated, and it came out to be 0.7846. So for our observed time and performance ratings, observed times were recorded for each element, of course, and we used, and they were adjusted using performance ratings ranging from 95 to 110%. So using these ratings, normal time and standard time were calculated, and we saw minor differences that occurred between each cycle, but there were no major anomalies that were observed.
Hello, my name is Sulaiman Malik, and I'll be talking about the analysis portion. So, once we reported all of our observed times per trial, we then multiplied that value by each trial's respective performance rating in order to achieve our normal time per task. Using our 10 observations per trial, we then found the average of those trials to be able to find our average normal time, which we would later then use to calculate the standard time taken to complete each respective task. So, in order to accommodate for basic needs, for example, the personal needs of the worker, basic worker fatigue or machine fatigue, and any other variable fatigue that one potentially would not see coming, we gave a total PFD allowance of 10%. So, the following bar chart here shows distribution, the variable time between each task, as well as how the normal time compares to the standard times. Normal times being in blue, standard times being in orange. Okay. Once we had the normal time per process, we then multiplied it by the PFD allowance increase in order to achieve our standard time per task. The total average standard time calculated ended up being 0.7133 decimal minutes. And the Pareto chart here shows the distribution in time ranging from what task that took the longest time to shortest. And we see that placing the filament in the extruder entry and heating the nozzle were the 2 tasks that end up taking the longest amount of time, although they only mounted up to being 33% of the total amount of processes done. They ended up taking up to 60% of the total amount of time.
Hello, my name is Blaise Paul. I'll be going over the findings portion. For this study, it showed that most of the steps were quick and consistent throughout each trial, indicating minimum variation. During the study, we were able to find 2 types of bottlenecks. The primary bottleneck occurred when we inserted the filament into the extruder, which contributed to the highest normal and standard time when compared to the other steps. The secondary bottleneck occurred when heating the nozzle, which caused a time delay, which is important required because during the process of 3D printing, you had to heat up the nozzle. For the variability in performance across the 10 attempts, it is seen that for the most part there was low variability, but during certain sections there will be high variability due to user error, such as inserting the filament. Oh, you might have to go back for a second.
I'm Parker Alanis. I'll be going over our recommendations based on our analysis of the 3D printing process. So, to improve this process, we recommend performing the steps of collecting and preparing the filament spool while the nozzle heats. This is because this is one of the second highest times throughout the entire process. However, it only requires the 3D printing personnel to begin the process, and then it will heat by itself. That means that during this time, they can perform other steps while this process completes, overlapping the times and reducing the overall time of the process. Next is the training needs. We recommend training the personnel on inserting the filament into the extruder, as this is by far the most complex step and takes the most time of the entire process, and has the highest variability due to human error. Lastly, equipment changes and layout changes. We can upgrade the extruder to one that is easier to insert the filament into, which reduces the delay and makes it easier for the personnel to complete this process, reducing the time and errors. We also recommend storing the filament within reach of the printer station, as this minimizes motion and reduces the delay between steps. In conclusion, most steps of this process are already quite efficient with low variability and quick times. However, there is high variability in the steps of inserting the filament. This leads to bottlenecks of inserting the filament into the extruder nozzle and heating the nozzle, being the top 2 times of the entire process, with inserting the filament being the highest variability. Our recommended improvements are performing the steps of gathering and preparing the filament while the nozzle is heating, since this will reduce the overall time. Focusing training on inserting the filament, as this is the highest variability step, making it the most complex and most prone to error. Upgrading the extruder to one with an easier to insert nozzle, which would also help with this variability. And storing the filament within arm's reach to minimize motion and reduce the delay between the steps. That concludes our presentation on 3D printing.